Ahmad Abdelrazaq. I don't think really Ahmad needs any introduction, but just for the formalities. Ahmad's been involved with Burj Dubai from, I'd say, inception until the completion. He worked as a designer on to start with, in the structural, and then he joined Samsung, who did the contracting for the building. So he is probably, I'd say, one of the most knowledgeable persons on Burj Khalifa. He's now serving as the chairman of American Society of Civil Engineers, SET, Tall Buildings Committee, and a lecturer at Seoul University, also a member of the advisory group and educational board of CTBUH. He has been named an Academy of Distinguished Alumni at the University of Texas. Mr. Ahmed.
Thank you very much for the nice introduction. And obviously today you heard me talk more of a general talk about what we engineers do and what we wish for. I think this talk will be very much specific to what we had done implemented in terms of the monitoring program that we did Burj Khalifa. Obviously, one of the things that before we decided on the monitoring system that we needed, we need to fully understand what the structural system of the building is, and to know where to locate the sensors to give us the optimum location and to get the best out of it. Obviously, we've been monitoring the building for wind, and also we've been fortunate enough to capture several earthquakes, far earthquakes, that happen around the region, both in Iran, Pakistan, and we've been able to trace these back and kind of look at the real performance of the building and compare it to. Okay, sorry. Obviously, many of you, you know, the project is located on the center line of metropolitan Dubai, and it was during construction. It was planned to be the highest building in the world, and now Dubai, since its start, has become the hub of tall buildings in the Middle East. It's a very large development project, consists of several parts. The total cost of the building is more than 20 billion US dollar, and it was completed, due to be completed at the time in 2008, some of part of it. And it consists of the residence, the business park, the old town, Dubai Mall, and most importantly, which is the centerpiece of the project, which is Burj Khalifa itself. Obviously, many of you probably know a lot about the project. It's a multi-use project, consists of a hotel, apartments, sky lobby, observatory. More or less, I would say it's a boutique office, not necessarily a very large office space that when we talk about communication, and obviously the spire and antenna. The total, the building is, total height is 828 meter, 160 floors. The design architect is an engineers, our SOM, and also the project manager is Turner, and supervision consultant and architect and engineer of record at Heiser Consulting. Again, as I spoke earlier, where did the concept of Burj Dubai came from? Obviously, we hear a lot about the Middle East desert flower, but obviously at the early planning stage, the project started as an all residential building. So it was designed from inside out, and as I mentioned earlier in my earlier lecture, Tower Palace 3 had on what we did there had a great influence in terms of what we had done on that project. From the early integration of the structural and architectural design concepts were extremely important. The architectural planning, it was originally an all residential building. That's the reason you see the plan that you see here today is more adaptable, as you can see here, more to the architectural layout, because initially it was, that was the intent of it, is hotel and residential. And we also wanted to maximize rentable space, wind engineering consideration, and integration with the architectural design concept on a proven and successful concept, maximize the effective depth, and also structural system continuity and modulation was part of the design. As most of you know, probably the building never, many of the member sizes never changed size. We never changed actually the form of the building at all. It was, we needed more area, we added more sections. And consideration to construction method was also implemented at the early design stage. As I mentioned earlier, also essentially the building and all reinforced concrete from foundation all the way to level 156. And above that, it became structural steel with composite metal deck. Again, as you can see here, the gravity, the member sizes that the total area that is needed for gravity is that, and this is how much material we provided. Essentially, we used an optimum use of material. And this plan here, it shows the modulation of the building as we went up to the top. Wind engineering was a major consideration again of the building, and Tower Palace again. We did a lot of work in there, and we brought it over here. And the wind engineering criteria and limiting the acceleration for all residential, one of the reasons why we did such a huge amount of wind engineering, because it was an initial and all residential building, and the acceleration criteria we needed to limit it within 15 milligis. Again, from the early strategic planning of the building, we needed to optimize the building shape, balance, mass, stiffness, damping, mode shape, disorganize the vortex shedding along the height, and variation of the building taper and reduce the wind sail and so on and so forth. And when we designing this building, you always wonder, do we really design this building for deflection, or we needed to limit the building in order to limit their acceleration as a serviceability criteria? Again, without dwelling, we spend a lot of time in the wind engineering, as I spoke earlier, a lot of wind tunnel testing, and RWDI was extremely involved in all the engineering, wind engineering aspects of the project with us from the very beginning. This one is a very important chart, probably Bill and RW and Peter Irwin has spoke a lot about. Initially, we had not very good situation, but later we were able to do some of these dynamic modification to the building and building orientation to bring the building without getting it into resonance. And so far, we have been measuring it for about 4 years, and it's been very good. Anyway, so we did a lot of wind tunnel studies, and the acceleration of the building, it is within, for a 10-year return period, is less than the ISO standard, and it was not an issue. So I will skip over those. Stack effects was another issue we had to deal with as an important design criteria. Seismicity, obviously, we've done a lot of work related to seismicity of the site by studying the geology of the site, regional tectonics, history of records of all the earthquakes that happen in the region, and the effect of near and far earthquakes, and also the area per UBC, it's seismic zone 2A, but in fact it's a little bit less when we did the seismicity study on the project. But essentially we still have to stick to the requirement that Dubai municipality had. Obviously here, again, most of the earthquakes essentially happen at the interface between the Arabian plate and Eurasian plate. And this is where most of the activities that affect Dubai in particular are located. So the question is, that's one of the reasons I think when we did the planning on the monitoring system, we had to keep in mind all of these activities that are related to the design of the building. Again, looking at this building, wind definitely controlled the design. And as you can see from this spectrum curve, the building is more falling within the control of seismic wind behavior rather than the seismic behavior. Again, skip over that. The structural system essentially consists of reinforced concrete core wall. Essentially, this takes most of the torsional, and practically this core remained the same size from bottom to top, never increased the size at all. And then as we needed more material, we channeled through the walls to these columns. And as most of you know, the building is more like bundled system. It's more like really an all core wall building, and practically we were able to calculate the overall deformation using a spreadsheet at the early design stage rather than this heavily computer analysis program. Practically most of the optimization of the building was done simplistically, not necessarily. And all of the columns here never changed size from bottom to the top of the building, remained the same size. We were able to manage the design that way. In concept, essentially what we had is the center core, and then we have the webs that were used to transfer, and these acted like flange to maximize the effective moment of inertia of the building. I'm sure many of you, and every 27 floors, we tied everything together. Practically, we eliminated any differential shortening between the elements, and the whole building was equally stressed, so we didn't really have anything to worry about. But at the same time, we also monitored the system to ensure strain measurement to look at the actual gravity load distribution into the building to confirm that. Again, the total building deflection it was at 159 is about 1.2 meter, but at the top of the spire, it's a little bit higher. Anyway, from here, obviously, some of the things that we implemented real-time monitoring program, including measuring of the building deformation due to gravity and lateral system. And also, we needed to also know everything about the building during construction. This is one of those buildings you don't know what's going to happen. And I didn't want to get into any time when somebody asked me what's happening here, and I didn't know exactly what the building is doing, whether it is lateral movement, whether it's related to strain, whether it is related to a creep and a shrinkage and a differential shortening, and so on and so forth. And also, so essentially we installed at the foundation level strain gauges and the piles and the raft. And also we surveyed the raft to look at the settlement of the building. And all of this information was used to calibrate the actually structural analysis model. But also we installed instrumentation to measure the wind climate. Obviously, the previous speaker, he still owed me some sonometers to work in the building. And the monitoring of the building, of the measurement of the lateral displacement, we needed because the building, as you know, have a different setback and constantly doing this. And the question, how do we keep the verticality of the building? So we needed to, and also not only from a behavioral standpoint, but looking at survey and installation and keep the building at this geometric center. And when something is that tall, you got the wind, you got the gravity, you got all of these, and how do you control that geometric center all the time? And at the same time, we also needed to look at the building behavior during construction. So the first thing we did is, as you can see here, install strain gauges, actually, believe it or not, at all these locations that you see over here in all the columns, almost 1/2 of the building. But it was located, strategically located around the area of the outrigger, 2 floors above the outrigger, 2 floors below the outrigger, and some strain gauges within the outrigger level to look at how the load is distributing itself as we build. And the whole system is essentially, unfortunately, the mouse doesn't work very well. But the whole system is essentially interconnected to a central data logger system or computer system down at the base of the building where we're able to download the data very well. And this is just an idea to show you what the strain, we were able to look at the behavior through the strain gauges, at the early stage during heat of hydration, increase in the strain as the things cooled down and started picking up again. This is again a logarithmic instrument, and this one here just shows the temperature rise in the building. So we're able to trace all the things that we needed to know about the building. And essentially we used geocon strain gauges into the building, as you can see on a floor by floor. There's just another aspects of some of the floor plans where we located the strain gauges. But obviously this is very important to do that, but at the same time we needed to develop our own construction sequence analysis model that essentially modeled every single activity in the building. And there were not really many available programs to do such a thing, especially related to the vertical shortening and also to predict the movement of the building with time, because it's going to displace and with time. And the question is, how do we keep it vertical and what kind of correction program we needed to do? So for every run we had to run, it takes about 4 to 5 days to make one run with a time frame, because every time we get the measurement of the data, we measured it, we looked at it, and then we looked at the survey, and we needed to predict what's going to happen next. So we constantly run the analysis model every, as needed, but almost every month. And sometimes if they are delayed in construction, we can also look at what the implication of the building has. We also measured the building settlement, which is approximately 50 millimeters, significantly less than what we predicted. But also we looked at what you see here is the survey. We surveyed the building very well to look at the, make sure the differential shortening will not become an issue for us or anybody else. But at the same time, we also measured the lateral displacement of the building with time, especially when we needed to lift it the pinnacle. We needed to make sure that the thing goes straight. And we were able to predict the movement within 5 millimeters of what we expected. But again, this is extremely calibrated structural analysis model that we used, and almost on a regular pace, almost every week I compared, every week, I compared to what's going on in the building. And mainly because of survey purposes, but also we needed to ensure that we don't run into any issues relative to verticality and the clearances. And because the clearances in the elevator shaft were extremely tight. And so anything we have to do, it would have been a problem. So we also did like a tilt meter system, and we enter that, with that system we were able to measure the actual movement of the building with time, almost instantaneously. We also installed a health monitoring system related to building acceleration at any time, instant of time. So if we have obviously wind load or earthquake loads, essentially we have everything connected to a central data logger system and one at 73 as a backup. So once we get the output out of the movement, such as acceleration, displacement, weather station, temperature, we were able to go back and actually measure what we predicted for the building, such as a spectra, mode shapes, damping, wind profile, track wind speeds, terraces, so on and so forth, at the terraces and everywhere else. And these are kind of, during construction, we installed also the same system during construction, because we were able to, also in case any event happened during construction for a period of 4 years, we also needed to know exactly what is happening with that. And today, as I mentioned earlier, from my office, I can see, what you see here is the acceleration of the building, the standard deviation and the maximum acceleration at the tip, and at tier 23, 160, 155, 123, 73, and also we get, as you can see here, the base acceleration at the top of the building, the displacement of the tower, and what is not shown here is the weather station. We did also look at the building frequency, and fortunately we were able to pick up all the higher modes of the building. And this is just kind of shows a profile what happened with time, movement of the building at a different location. For example, what you got here is this one is there, and related to the color relative to the mass. We also got data in terms of the wind speed along the height of the building and directionality of it. So it also helped us a lot during construction in terms of CPP and Notre Dame has been extremely helpful in developing the system with me here. Again, we captured an earthquake that occurred over here in Iran, which is roughly pretty far, not too far from Dubai. But because of as most of you know, the long period earthquakes generally do not attenuate very easily. And you can feel them very easily, especially in tall buildings. And then we captured all of these records, the first shock, the second rock. And then the magnitude was not so high, but we captured others that are significantly more. And we actually got all of this information online. Then we took the pace acceleration and time history record, and we compared that against what we measured. And the correlation was really excellent. So, so with that, I think this is probably, it has been extremely successful case for us, and pretty much the analysis that we've done, it covers some of the issues that the speaker this morning talked about related to long, very far earthquake with the low frequency. So anyway, these are just also we took that because the displacement is not very difficult to calculate because we have the actual pace acceleration at the building, which is time history record. We're able to look at the actual displacement actually of the building, and the correlation again, it was pretty good. And with that, I think I'd like to just in my talk, this is comparison of the displacement at different level along the height of the building. Again, we made a comparison between the building acceleration, building period versus what we predicted, and it was very close. Okay, and this is just here to show you some of the pictures, reference photos for the building of the Burj, using a very heavy equipment that needed a special design and a special requirement, and limitation on the cable length was one of the biggest issue we have. Obviously, we have temporary hoists that are high capacity to transfer a lot of things in it, equipment, concrete placing booms and jump hoists. Just some photos related to rebar work. And during construction, one of the challenges we had in the outrigger is we had a lot of steel in them. Sometimes it was very difficult to use. So I replaced all the structural steel, all the rebar with the structural steel sections. That was absolutely necessary to make sure that the behavioral response of the building is not changed also. Obviously, the elevators are also very special. They are the fastest double elevators, 10 meters per second. The longest elevator shaft is about 508 meters, and the most stopped elevators and so on and so forth. Mock-up for the cladding, installment of the cladding. Again, as you can see here, flat plate construction was really a nice thing to have. On this project that allowed the fast construction cycle of it. And when you look at the top, from the top of the building, you can see Dubai, some of these buildings are not very small, they are very tall, and this is just some of the reference photos we have. Again, I hope it works. Something wrong? Okay. This is here for me with the team from CPP and myself installing the accelerometers at the top of the pinnacle at 828 meters. So you have to climb up about 200 meters up into this small thing, but it was pretty exciting. And with that, I thank you for your attention, and if you have any questions, please let me know. Okay, thanks. No
the questions later.
Okay.
Well, thank you, Ahmed, for taking us through a beautiful tour through Burj Khalifa.